Hey guys, how we doing? All right, we're back at it. So you just finished up, hopefully simple events, probability of simple events, and I hope that was good. You can tell I have the same decoration and the same shirt. This is the artwork from the Tlingit people in Alaska. They're the people that are famous for totem poles, those wooden poles that have like eagles and orcas or killer whales carved into them. Kind of fun. But I've been wearing it for 3 days. No, I haven't. I've been here like 3 hours working on stuff and trying to grind it out so I can get you ahead. All right, I think we're ready. Interestingly, I almost taught 10.6 and 10.7 as a double because I almost want to teach 10.7 before 10.6. But I didn't want to do that to you guys. I felt like you guys have enough to do, so I backed off. But 10.7 kind of already did it. So I just want to show you a little bit of what it is, get it into your notes, and I'm going to release you quick into the homework. So let's switch cameras over. If you could add to your notes, you should be in your math notebook if you're trying to get full credit for this class. And I would ask you to label 10.7 theoretical and experimental probability. Big words, right? Theoretical, which is mostly what we do, and experimental, which is mostly what science does. Probability. I don't know. Maybe we do experimental just as much. All right, theoretical and experimental probability. Let's define those two words. At the core of theoretical is actually theo, which is God. It's where we get the word theology. But this is like as in not it is God, but it is controlled by God. It's like we think about it, and based on our understanding that God is around and God is going to keep the world working the way the world's always worked. This is like basically Colossians 1. Jesus is upholding everything, and that's why algebra will work tomorrow. If everything stays true in the universe because God is good, then I can have a theory that will be true. So I'm stretching a little bit, but helps me remember. The theory is that when I flip a coin, because there's a heads option and a tails option, some building or something, who knows? There's a heads option and a tails option, then there's usually one way to get what I want and two possible outcomes. So my theoretical probability is 1/2 or 50%. That's theoretical. Experimental is the scientific method. I'm going to set some parameters. I'm going to control everything I can control, and then I'm going to try it. So let's come up with something else that has a theoretical event. Let's do, this was the probability of an even number. The probability of an even number, what are my evens? 2, 4, 6 on a, here we go. Probability of an even number on a number cube would be the 2 or 4 or 6. So that's 3 ways to win at a 6, which is equal to 1/2. So there's another example. We'll roll that down. Now let's look at it experimentally. So experimental, we're just looking at experiment. This is the scientific method. And that means one of our steps in the scientific method is data collection. So we are collecting data on this one. That is the difference between theoretical and experimental probability. Experimental probability requires data collection, and theoretical requires thinking. So theory comes from data collection and thinking, but theoretical and probability just means thinking. Experimental means do the experiment, collect the data. So let's go ahead and do that. What is the probability of 2, 4, or 6? Or another way to say that is the probability of an even number on a single dice roll. Oops, let me get these out of here. Yeah, I have all these meetings that I can't attend anymore because no one's here. All right, so we're looking at these, right? 5. Didn't happen. So I'll put my evens over here, my odds over here. I'm just going to create a tally sheet for myself. So I got an odd, an even, an odd, an even, and an odd. An odd and even, an odd and even, and an odd. Keep going at it. Even, odd, odd, even. Even, odd, odd, even. Okay, looking pretty good. Let's do two more. Even, even, even. Let's go till I hit an odd. There we go. All right, so for the sake of math, actually, I might want to keep going. Let's do six more. Odd, even, odd, even, odd. Two more. Odd. Okay, let's organize a little bit. All right, so what do we got? We got 8 evens and 12 odds. So if you were rolling dice in any game ever, you would definitely want to have odd numbers. Put your money at the casino on those odd numbers. No, theoretically, the probability is half. What's the probability of even? In an experiment, it's 8 out of 20. Or 4 out of 10. Or 40%. Oh, so we got a 40% and a 50%. So what's going on? Theoretical and experimental don't show out the same. But if you get a larger sample size, if you use large samples, you will get closer and closer to the theoretical probability unless you've missed something or you've miscalculated, you don't understand the situation the way it actually works, and you shouldn't yet be thinking. You don't have enough information. But you need large samples to get accurate probabilities through experimentation. Over time, you'll get closer to 50%. Let's keep going, and I'm going to use purple for this. Let's keep going. Odd, even, odd. Odd, even, odd. And then that last one's even, it's a 4. Even, odd. Even, odd. Odd, that's even. So odd, even. There we go. And I'll transfer these two over here for 1, 2. Okay, so now what is it? Now it's 15 to 17. Notice that's getting closer together. It used to be a gap of 4 with small numbers. Now the numbers are bigger and there's only a gap of 2. Over time, you will continue to see those come together until they're very, very close to 50%. It'll just take time. So larger samples, that's the secret. Now, as you're thinking about these, the real purpose of learning any of this stuff is to predict the future. So let's do A here. I tell you the probability that, the probability that you go to the airport and your flight is canceled right now is pretty high. Let's give it 72%. And we're going to tell you that from CEI, which is Chiang Rai International Airport's 3-digit international code. So I'm going to tell you there are, let's go 76 flights today. 76 commercial flights for people that might show up and want to ride are coming out of the international airport in a day. So that means, what does it mean? How many flights would we expect to fly? How many flights would fly? All right, so we've got to answer this question, but there's a lot to this question. So we want them to fly. What does that mean in terms of canceled? That means not canceled. Oop, is it 2 L's or 1? I think it's 1. Nope, it's 2. Looks bad. All right, not canceled. That's our real curiosity. So what's the probability of not canceled? Well, it's everything else. So that would be not 72, which is 28. So we want to know 28% of 76 flights. Or, and you should remember this by now, you could solve this a number of ways. In this case, you could do 28 hundredths of, usually means multiplication, 76, and you would have the number of flights that will fly. And of course, the other way to do it, which will work all the time, and I recommend it highly, is you use the symbol to mean exactly what it says. Divide by double zero. So divide by double zero, and 28 over divided by double zero. And that we're going to say is equal to, we're not asking how many flights out of 100, we're asking how many flights out of 76. F for flights. Go ahead and solve that, and of course you'll land in the same spot. I'll go ahead and do that. Let's go 28 times 76. Hopefully you remember that. Times 76 equals divided by 100 equals 21 and 2, or I guess 3/10. But we're not going to get a tenth of a flight, so we're going to go with 21 flights will fly in one day from CEI. Okay, why did I capitalize that? All right, I think that's it. If you can handle those skills, you are ready to go. If you would like to stop the video now and transition directly to the homework, then please skip to the end of the video or look at the assignment page and you'll see it there. That's going to be my normal pattern. But I would encourage you to participate along as I do some of the guided practice. So for the guided practice, the table shows the results of an experiment in which a number cube is rolled. Find the experimental probability of rolling a 4. Then compare it to the theoretical probability. Okay, so here's number 1. The number of times a 4 was rolled was 3. So the probability of a 4, I'm going to put a TH up here to say theoretical, is 3. But out of how many? Well, it looks like 7, 10, 15. So that reduces down to 1/3, which I know is 33 3/10%. You'll want to memorize that one. It should be part of what you do. Now, what should it have been? Now, if this is an even and fair number cube, if it's even and fair, all the sides are the same, all the corners are the same, then this should have worked out to I'm sorry, that was experimental. It should have worked out to an theoretical probability of 1/4 out of 6 possible outcomes, and 1 divided by 6. You don't have to do the percentages, but 1 divided by 6 equals 17%, or 16 7/10% when I round off. Okay. So how would I compare them? Well, I would say I keep capitalizing things, sorry. The experimental probability is about, how much higher? 17% higher than the theoretical probability. Ta-da, number 1. Boom, done. Not too bad. All right, let's look at number 2. Isaiah flipped a coin 40 times. He found that the coin landed heads up 18 times. Find the experimental probability, then compare it with the theoretical probability. So 18 out of 40 was, what is it? Heads? Yeah, so the probability of heads 18 out of 40, which is the same as 9 out of 20. And if I multiply that by 5, I get 100. Multiply by 5, I get 45. And then if I think about the theoretical probability, then I would expect it to be 1 out of 2 even and fair outcomes of the event, and that would produce 50 out of 100. So how would I compare them? I would say the theoretical probability is 5% greater than the experimental probability. All right, I do want you to spell the words. Notice up here, I took the time to do it. I'm a professional mathematician. It's my degree. It's what I do. I need you to write them. I wrote them, you write them. Write them out. I'm doing this because some of you have asked me to speed up the videos, and I'm trying to do that but still give you content. So there we are. Let's look at number 3. Without looking, Dolores took a handful of multicolored candies from a bag and found that 40% of the candies were yellow. Suppose that there were 375 candies in the bag. How many can she expect to be yellow? So she's thinking that there are 375 candies. Okay? And 40% are yellow. If 40% are yellow, that's pretty easy. That means 40 out of 100 are yellow. But I don't want to know out of 100. I want to know out of 375. So C for candies, or better yet, Y for yellow. A little bit of math later, right? Multiply an angle, divide by the other. Multiply an angle, divide by the other. Multiply an angle. 40 times 375 equals 15,000. Divided by 100. Don't even need to do that really, but it's 150. We'd expect 150 yellow candies in the bag. Boom. Got it. All right, looking good. Last one, 4. The table shows the results of a survey about the most popular pets among 7th grade students. Out of a similar group of 320 7th graders, notice it's a similar group, so this is representative and we assume it's random. Predict how many would choose cats as their favorite. For this one, rather than show it all to you, I'm just going to give you the proportion. So as I'm looking at this, I'll try to put it down here where you can see it. So the number that would choose cats is 11 out of, 23, 29, 34, 40. 11 out of 40 chose the cats, but we don't want to know out of 40. She wants to know out of 320. Now this one I know I could multiply, but I'm not going to do that. I could see that here 4 times 8 is 32. So I could just go times 8, and I'd figure out immediately that 88 students would choose cats. But just to do the process the proper way that always works, I'll go 11 times 320 equals divide by 40, and what? It's 88. Who knew? Besides everyone. All right, I think we're good. So it's time. If you just fast forward, this would be the time. Hey, stop the video. Homework time. The homework here, I'm going to ask us to look at, this is 10-7. I'm going to ask you to look at, I think I want to do 5 through 15. Yeah, I want to do 5 through 15 odd tonight. So again, I want to do 5 through 15 odd. 5 through 15 odd, and I will write that in the assignment notes as well. So for those of you that are wanting to see the book, I think I may have forgotten that in the last assignment. I'm sorry. But here's 5. And down below, there's your number 7. Thank you, Miss Wendy. I'm not alone. There's someone else here. Miss Wendy just brought me something that was nice. There's number 7. After 7 comes 9. You need that table right there. And then 11, you can already see. There's 13. And if I scoot it right, there's also 15. So 5 through 15 odd, and you're ready to go. Here come the answers. On 10, 7, 5 through 15 odd. There you go. Hey, you guys are awesome. We're still grinding it out. We're making do. Hey, I want to pray for your families as we go. I really want you to spend time with your family. Learn how to reconcile conflict. Learn how to pray. Learn how to be creative in a space that's limited. You're stuck in your house probably. So God, help us to be creative people. Help us to take care of each other. Help us to love our families that you've given us, even when those families are hard. Help us to show love and to find ways to enjoy and to bring joy. We love you, Lord. I ask this in Jesus' name. All right, you guys, we're out. See you next time.